I'm going to go through a proof of this proposition here, which states that if K is a closed subset of some compact topological space X, then K is compact as well. So let's go ahead with the proof. So let's let X be a compact topological space. And what else are we assuming? So K is a closed subset of X. So we can let K in X be closed. And we want to show that K is compact. So somehow we have to use the fact that K is closed and the compactness of the ambient space X. So let's write down a few facts. So, well, since K in X is closed, well, by definition, the complement of K in X is open. So that's just straight from the definition. Now we want to generate some open cover for K with some open sets. So now let K, well, let's write it this way, let the union, so I over some index set I of some open sets UI, and these sets UI are all open in X. So we're taking some arbitrary union of these open sets, and this is going to cover the subset K. So let's say UI open in X. Let's say this is an open cover of K. So eventually we want to show that, well, the definition of compact says that every open cover admits a finite subcover. So by taking an open cover, we want to show eventually that from this we can generate a finite subcover. And that will guarantee that K would be compact. So here we have this open cover of K. So let's leave that for now. So what we want to do is use the compactness of X, right? So I'm going to rewrite, or kind of transition to the general topological space X and find a cover for that, right? Because then I want to be able to use the compactness of that space. So let's write this down. So now, so I could rewrite X as, this might seem a little bit silly at first, but bear with me. So I'm taking the complement of K in X, and if I want an equality, I'll just have to get K back. Right? So this is quite obvious. You're just taking away K and chucking it back in. Well, here we have X So we have k involved in this expression here. So that's the point. And well, what was k? Well, so k, we found a cover for k, an open cover. So now I could write this like this. So let's say x, k. So I'm going to union. So this here, well, this was a cover for k. So therefore, I could write the union over I of these ui's from earlier. Right. So this here, right, is an open cover of x. So open cover of x. Right, because x, which equals this, is contained in this expression. Well, it's an open cover of x. Well, since we have this here, well, we showed earlier that this is open, and then we're taking a union of all, or of another union of open sets. So yeah, it's going to remain open, and it covers x. So we have an open cover of x. So since x, complement of k and x is open, and the union of opens is open, so that goes without writing. So now we use the compactness of x. So since x is compact, well, we found an open cover of x. It has a finite subcover. Right? So since x is compact, this cover of x has a finite subcover. So what is it? So let's write x covered by, well, because this could be an infinite set. So this is one set here. We take the union, and we want to take finitely many of these. So we take the union of, and we'll just use a new index here. So it's ui 1 union ui 2, and do this, but we stop at ui n for some n, right? And this is finite and still covers x. So now, well, we know that this k is a subset of x, and well, if you take the complement of k in x and you intersect that with k, well, this is just obviously empty. So in a sense, we can kind of remove this, and what's left over still is going to be a cover for k, right? So k is covered by pretty much everything else here. So K is covered by UI1 up to all the way to UIN. So all these open sets here, so it came from the cover, the open cover of K earlier, right? So we took UI open in X, and the union of those open sets covered K, and we see that when we take finitely many of them, we still have a cover of K, right? So that's pretty much the definition of compact, where you take any open cover, it has a finite subcover. So since our choice of UI was arbitrary, this works in general. So K is covered by the union of these open sets up to N. So what can I write? So this is a finite subcover of K. So we pretty much get that K is compact, which was what we wanted to prove.